We're now going to look at another classic historical problem, the n-body problem, in this particular case with n equals 2. The basic idea is, let's say you have a number of masses, in this case 2, sitting in space, which have, I don't know, some velocities, and they're acting under the influence of some mutual force, like gravity or electrostatic attraction or repulsion. How would they move? If you just have one object moving in a gravity field, you can solve that. It turns out you can actually solve using calculus two objects moving in their mutual gravity. When you get three or more, it turns out it's actually impossible mathematically to solve them numerically. Mathematicians tried for the best part of the 18th and 19th century, till eventually towards the end of the 19th century it was proven by Henri Poincaré that actually it's impossible to solve. That was the foundation of chaos theory. But anyway, for today's worked example, we're going to just deal with two particles moving under the mutual gravity, and we're going to solve it numerically. And let's say it's gravity. So we've got object A, and it's got a mass ma, and object B with mass mb, and that's a position vector A, and that's a position vector B. Now we know that the magnitude of the gravitational force is equal to gravitational constant ma mb over the distance between them squared. But that's a scalar equation. We need a vector equation because we're going to need to know the direction of the force, not just how strong it is. And we know that the gravitational force will pull them towards each other. So what we can do is we can look at the vector from A to B. We'll call that r, the displacement vector. So we know that r equals b minus a. And we can then rewrite this force equation in vector form. So the vector force on B, so that's the force that A applies to B, is going to equal G M A M B over mod r squared, and it's going to act in this direction. Now that direction would be r hat. It's a unit vector in this direction, so we want minus r hat. So r hat is just telling us the direction. That's what unit vectors do. They just point the direction. This tells us how strong the force is in that direction. The minus sign says it's pointing towards the first object. And similarly, the force on A due to B is given by G M A M B over mod r squared. And this time it is pointing that direction, so it's not minus r hat, it's r hat. And that will give us the size and direction of the two forces. Now there's one trick we can apply. We know that r hat equals r over mod r. So if we substitute that in, it equals minus g MAMB over mod r cubed r. And it's now the vector r, not the unit vector r. And similarly down here. So you can see, as you'd hope, that these two forces are equal and opposite, so that it agrees with Newton's third law. Our step equation then will just be that the new velocity equals old velocity plus acceleration times delta t, where acceleration is f divided by the mass of the object, and the new position equals the old position plus velocity times delta t.